This section is about the equations of lines and planes. In the two-dimensional plane, we pick some point and some slope, and then we have what we call point-slope form, and it can be written in slope-intercept form. Similarly, if we're going to look at a three-dimensional space, let's get a clean space here. If we look at a three-dimensional space, so here we have x, y, and z. X, y, and z, not necessarily in that order. So picture that coming towards me in this first octant, but it's not going to quite look that way. But in this first octant, let's take a line. Here we have a line, and from this, on this line we have some point, and the point is point sub 0, so it's x0, y0, z0, and then we have some vector to help us find direction. So let's put this in red. So here we have some vector a. So this is the vector a and point p sub 0. So here we have a line and a direction, because the vector gives us direction, and we can use that to help describe our line. Now what we're going to do in this process is we're going to call this point, this vector right here, we're going to call this r sub 0. And then if you look at this, we have another vector, the sum of the two. So this vector right here is vector r, and vector r is equal to the vector of r sub 0 plus a sub 0. Now r sub 0 could be this point here at the back. I'm going to draw it in with pencil because I can't erase in this program. So it could be over here. R sub 0 could be over here. It could be over here. It could be over here. We have lots of r sub 0s that could be possibilities all the way touching that line. But what is important is that parallel to A, we have some vector V. So here, parallel to A, we have some vector V. And that's going to be helpful because since V is parallel to A, since the vector V is parallel to A, then we can say that A is equal to some multiple of vector V, where T is a scalar. Now, this is really cool because this goes back to your parametric equations that you learned in Calc 2. Let's make a note over here. Let's make this a note. Oops, let's make this a note. And here we have that vector A is parallel to vector V, parallel using that geometry notation that we had before. So we can say that A is some multiple scalar of V. Now the way that comes in handy is we're going to say vector R is equal to R sub 0 plus the scalar T times the vector V, and T is our parameter. See, parametric equations. I love parametric equations. It's really cool. Now what's interesting to note is if T is greater than 0, then our point P is to the right. P is to the right of R sub O and P sub O, of vector R sub O and point P sub O. So if T is positive, let's go back over here. If T is positive, then that means our R sub O comes over here. T brings that line over here somewhere. And then if T is negative, we're going to find that, let's do this in a different color. I think this purpley color might work. Not really, let's go with the blue. So if T is negative, then this vector comes over to the left side of P sub O. So that's just interesting information. If T is negative, then P is to the left of R sub O, vector R sub O, and point P sub O. So you can move this around just like you could in 2D space, but it's really interesting to look at. So we're going to take this equation here. This is our beautiful equation of our line, and we're going to make a note of this. So this is our big note here. Note R equals the vector R sub 0 plus T times some vector V. And so let's bring it back up here. We have r equals r sub o plus t times the vector v. Now, our r is going to be, let's come back in here. So r equals some vector x, y, z, because it goes to some point over here, which is some point p at x, y, z. So you can see how it goes from the origin to some point p. And let's make a note here, r equals x, y, z. And then r sub o, it goes from the origin to point p sub o. So it's x sub o, y sub o, z sub o. And then we have vector v, and it's parallel to vector a. We're going to call it ABC. It is the direction of line L, so we're going to call it ABC. So then if we use our note, we can say that r, which is vector x, y, z, equals r sub o, which is x sub o, y sub o, z sub o, plus t times ABC. So then we can say x, y, z equals x sub o plus ta. Our second component is y sub o plus tb. And our third component is z sub o plus tc. Now this gives us three parametric equations. And I'm going to scroll over because I would like to lose the stuff at the bottom. So this gives us x equals, look at it component-wise, x equals x sub o plus ta, y equals y sub o plus tb, and z equals z sub o plus tc. So these are your parametric equations that you're going to use. So let's make a note here. It has stuff above it. So we're going to keep this here. Do you see how these component-wise go together before I move on? This equals this, the second component equals the second component, and the third component equals the third component. So we can make a note. Let's make it over here, note. A parametric equation, parametric equations, because there's more than one, parametric equations for a line through the point P sub o, which is x sub o, y sub o, z sub o, and parallel to the direction vector. We should probably label it the direction vector, to the direction vector. A, B, C are x equals x sub o plus ta, y equals y sub o plus tb, and z equals z sub o plus tc. So that gives us our three parametric equations. What's important to notice is you're going through a point P sub o, and you have a direction vector ABC. And pay attention to the fact of where those go. Those both go on the right side, so you have a very general set of equations. So let's look at an example of one of these. Okay, the directions say find a vector equation and a parametric equation for the line passing through the point 513 and is parallel to the vector I plus 4j minus 2k. Notice they have bold instead of vector notation because that's what the book does. So let's start off with writing our three parametric equations. Let's say x equals x sub o plus ta, y equals y sub o plus tb, and z equals z sub o plus tc. Now remember that my point right here is x sub o, y sub o, z sub o, and the direction vector is a, b, c. So we're going to say x equals x sub o, which is 5. A is 1, so we just have a t here. Our second equation is y equals, the y sub o is 1, plus, and b is 4, so we have 4t, and z equals, the z sub o is 3, plus the t is our variable, and our constant is -2. So we're going to say minus 2t. So those are our three parametric equations. And that's part A. Part A says find the three parametric equations. Now part B, the hard part here is remembering which one is x sub o and which one is ABC. But remember that ABC is a vector, and x sub o, y sub o, z sub o are your points. So part B says find two other points on the line. So this is part A. Part B, let's let t equal 1. So that means I have the point 5 plus 1 is 6, and 1 plus 4 is 5, and 3 minus 2 is 1. And let's also let t equal -1. And when we do that, 5 minus 1 is 4, 1 minus 4 is -3, and 3 plus 2 is 5. You could pick other things. The textbooks tend to pick 1 and -1, so I'm not sure what WebAssign is going to handle there. They may tell you specific t-values to choose. One thing to make note of here is that these are not unique. So if we change the p sub o, or if we change the parallel vector, the equations could change. Let's say we used, instead of using 513, we used the 651. If we use 651 here instead of 513, then our alternate equation would be, you would say x equals, the first point is 6, and you still have 1t. The y equation would be y equals, we now have 5 plus 4t. And the last equation, z equals 1 minus 2t. Then, yes, there are lots of ways we could write this equation of a line, just like you could in two space, but make sure that you use the point and the direction vectors that you're given up, like up here. Okay? Before we move on, these equations would also be different if we had a different vector instead of ijk, instead of I plus 4j minus 2k. If we picked a parallel vector, we would have a different answer as well. But you use what you're given and go with it like that. Generally, v is the vector ABC used to describe the direction of the line L. Then, therefore, the points A, B, C, the scalars, are called direction numbers. Direction numbers of L. Since any parallel vector could be used, then any number proportional to ABC could also be used as a set of directional numbers. So these are called direction numbers. They give us the direction. That kind of makes sense. Another way to describe L is to eliminate the parameter t from the equations. Now, if a, b, and c are all not equal to 0, we can solve for t. Think about this one. I'm going to work this one out greatly. So this equals ta. So then x minus x sub o over a equals t. So we can say t equals x minus x sub o over a. Similarly, not y equals, similarly, t equals y minus y sub o over b. And thirdly, t equals z minus z sub o all over c. Now, since they all equal t, first of all, this is another way to describe the line L. We have our direction numbers up above, and we have these equations. But if you think about the fact that they're all equal to t, you can say x minus x sub o equals a over a, which equals y minus y sub o over b, which equals z minus z sub o all over c. So these equations are called symmetric equations. Of L. In my notes, I would like it to say that since you have these equations, then these equations are the symmetric equations of L. So this example says find parametric equations and symmetric equations through the points A, which is 2, 4, negative 3, and B, which is 3, negative 1, 1. So the first thing we need is a direction. We need a point and a direction vector. So let's let our vector V be equal to AB. So 3 minus 2 is 1, negative 1 minus 4 is negative 5, and 1 minus negative 3 is positive 4. So this is our direction vector, and this is equal to ABC. So keep that in mind. And we can choose either of these points. I'm going to choose point A. Then our parametric equations are x equals the point, which is 2, plus 1t, y equals the y value, which is 4, minus 5t, because that's our b. And then z equals the z value, negative 3, plus c, which is 4 times t. So that's our parametric equation, part of part A, super nice. And then the symmetric equations, we're going to solve for t. So that means over here, we're going to say t equals x minus 2. On the second one, we're going to say t equals y minus 4 over negative 5. And then t equals z plus 3, and we're going to divide it by 4. But in the symmetric equations, you set them equal to each other. So x minus 2 equals y minus 4 over negative 5 equals z plus 3 over 4. So that's the second part of question A. Question B says, at what point does this line intersect the xy plane? Now remember, in the xy plane, z equals 0. So that's a given to us there. Let's plug that into our parametric equation up here. So we know that z equals 0. That's going to help us solve for t. So we're going to say t equals 0 plus 3 over 4. So t equals 3/4. That's the easiest way to go. You could have plugged it in a different manner and done it a little more hard, but it's not necessary. Oh, you could have plugged it in up here, but it's pretty easy to plug it in over there. So t equals 3/4. And we're supposed to find the point where we intersect the xy plane. So we want to plug that into the other two parametric equations. Now I'm going to choose the two from the blue box up here. So we're going to say x equals 2 plus 3 over 4, which is 4 over 4 plus 3 over 4 is 11 over 4. And then y equals 4 minus 5 times 3 over 4. So I get 4 minus 15 over 4, which is 16 over 4. Minus 15 over 4 is 1 over 4. So the point of intersection with the xy plane will be the point 11 over 4, 1 over 4, and 0 for z. So that is our point of intersection for the xy plane. Part B, done. Just a note to make at the bottom of this page. Let's make a note right here that you can find a line segment. So we're going to say the line segment from R sub O to R sub 1 is given by the vector equation. R of t equals parentheses, that's a vector R. R of t is given by parentheses 1 minus t times R sub 0 plus t times R sub 1, where t is between 0 and 1. Now, we didn't use it. We're not planning to use it. There's a proof for it. But if you want to find the line segment, that's a way to do it. Moving on. So example 3 is a cool example. show that lines L1 and L2 with the given parametric equations are skew lines. Remember skew lines from geometry? They don't intersect and they're not parallel, so they don't lie in the same plane. So we haven't done a whole lot with skew lines, but here they are. So first of all, we're going to determine if they're parallel. Remember that in order to be parallel, they need to be multiples of each other. And this L1 to L2 is definitely not a multiple. So we can say they're not parallel. There's no multiples for any of them. So we're going to say L1 is not parallel to L2. Since not proportional, because you got to have a reason. You can't just say it's true since they're not proportional, since the components are not proportional. All right, so now let's talk about if they intersect. If line 1 and line 2 intersect, then there is a T and a S such that it makes all the equations true. Or they make all the equations true. The word equations there looks a little funny. It's okay, let's run with it. All right, so we know that x equals 1 plus t and x equals 2s. So let's set them equal to each other to find our point of intersection. So 1 plus t equals 2s. For the y's, we have negative 2 plus 3t equals 3 plus s. And for the z's, we have 4 minus t equals negative 3 plus 4s. Now we're going to rewrite these so we can have systems of equations. I'm going to say 1 equals 2s minus t. And then I'm going to bring the negative 3 over. I'm going to bring the 3 over as a negative 3. So negative 5 equals, we're going to keep the s minus 3t. And then 4 plus 3 is 7 equals 4s plus t. Let's take the top one and the bottom one. So we have 1 equals 2s minus t. And on the bottom, we have 7 equals 4s plus t. So if we add these, we get 8 equals 6s. So s equals 4 over 3. So now let's plug that into, let's say the bottom one. 7 equals 4 times 4 over 3 plus t. So 7 equals 16 over 3 plus t. So if we subtract it over, 21 minus 16 is 5. So 5 over 3 equals t. So if these lines intersect, we can plug them in. We can plug this value of s and t into all of the equations and it should work. We haven't used the middle one yet. So let's pick up the middle equation, which says negative 5 equals s minus 3t. So negative 5 equals s, which is 4 over 3, minus 3 times 5 over 3. So we get negative 5 equals 4 over 3 minus 15 over 3, which says negative 5 equals negative 11 over 3, which is not true. Since it's not true, the points don't intersect. The lines don't intersect. Therefore, L1 and L2 do not intersect. Now, since they don't intersect and they're not parallel, therefore L1 and L2 are skew lines. Those 3 dots right here mean therefore, so we can always use them as therefore, are skew lines. So if you need to show that they intersect, you show that that point works in all of them. But this right here shows no point of intersection because we found the point of intersection for these 2 lines up here. This is our point of intersection for those two parametric equations, but the point of intersection does not work in the third. Therefore, the lines must be skew. A line in space can be determined by a point in a direction, but a plane is not quite that easy to describe. So we're going to talk about planes. So when we look at a plane in space is determined by a point in the plane. We call it P sub 0, which is x sub 0, y sub 0, z sub 0 in the plane, and a vector that is orthogonal to the plane. So we're going to call that vector n. So we're going to have a point sub 0, which is x sub 0, y sub 0, z sub 0, and vector n, which is the normal vector. It has an interesting name. Normal means perpendicular. So this is an orthogonal vector. And it's orthogonal to the plane. It's also called a normal vector, and that's why it's n. So if we let's pull in a picture here. So if we let P be some arbitrary point on the plane here, point P, and R sub O be the position vectors of P sub O and P like they were before. So here you can see R sub O, and here you can see vector R, as I don't do that well. So here you can see vectors R and R sub O. Let me label them this way. Then the vector R minus R sub O is the vector that represents the vector from P sub O to P. And then the normal vector n is orthogonal to every vector in the given plane. Now we know it's orthogonal to R minus R dot 0, R minus R sub 0. So then we know that the dot product, since vector n is orthogonal to this vector R minus R sub 0, that means the dot product has to be 0. So that's a really cool notation there. And it can be written as n dot R equals the vector n dot the vector R sub 0. And this is called the vector equation of the plane. This one is used more, so let's label it that way. The vector equation of the plane. Now we can put this into nice pretty things because we're going to let n equal the vector ABC. And just like before, R is going to be the vector XYZ, and R sub 0 is going to be the vector X sub 0, Y sub 0, Z sub 0, because they all come from the origin. So then we can say that n dot R, so ABC dot XYZ equals ABC. We could go with either version here, the top one or the bottom one. We're going to go with the bottom one. And then we have X sub 0. There's a dot here, and I did put a dot over there, but I didn't fill it in here well. X sub 0, Y sub 0, Z sub 0. So let's go ahead and do the dot product. So we have AX plus BY plus CZ equals AX sub 0 plus BY sub 0 plus CZ sub 0. Can we skip some steps and say A parentheses X minus X sub 0 plus B parentheses Y minus Y sub 0 plus C parentheses Z minus Z sub 0 equals 0. So this is our scalar equation of a plane. So let's make a note here. Note. So we can say a scalar equation of the plane through a point P sub 0, which is x sub 0, y sub 0, z sub 0, and with normal vector n equal to vector ABC, is a times x minus x sub 0 plus b times y minus y sub 0 plus z times z minus c times z minus z sub 0. You can see that. You can often, because these are sub-zeros, there are specific points. So that means we can end up with a general form. We can rewrite and put a general form. ax plus by plus cz plus d equals 0. And this is called a linear equation in xyz. The linear equation in xyz. Conversely, that means your if then goes the other way. If a, b, and c are not all 0, then the linear equation 8 represents a plane with a normal vector of a, b, c. So you can see that the values here are the values in your normal vector, and that kind of makes sense. So let's look at an example of this. So this says find the equation of the plane through the point. And with normal vector here. Now, I really like to label my point sub-zero to be 2, 4, -1, and vector n equals 2, 3, 4. So let's go ahead and plug that in. So if you think about the equation, I have n dot parentheses r minus r sub 0 equals 0. That's the easiest way to think about this equation. And so my normal vector is 2, 3, 4. Times my vector here I'm going to go ahead and put vector notation and say x minus the x value, y minus the y value of 4, and z minus the z value of -1 equals 0. So now I have 2 times x minus 2 plus 3 times y minus 4 plus z, which is 4 times z plus 1 equals 0. Now this is our scalar equation of the plane, and you have to look at which form they're looking for. So this is our pretty scalar equation of a plane. Now they may want it in a linear form. So let's go ahead and distribute. So we say 2x minus 4 plus 3y minus 12 plus 4z plus 4 equals 0. So 2x plus 3y plus 4z. And then we're going to combine the -4, -12, and +4 to be -12 equals 0. I really like equals 12, but the textbook tends to lean towards -12 equals 0. I'm really okay with either way. So this is the plane. Now think about your intercepts. And part B says find the intercepts and sketch the plane. So to find intercepts, we let the other variable be 0. So to find the x-intercept, we're going to let y and z be 0. So we have 0 and 0. So we're going to say 2x equals 12, so x equals 6. To find the z-intercept, we're going to let the y-intercept, we're going to let the other two be 0. So 3y minus 12 equals 0, so y equals 4. To find the z-intercept, we're going to let x and y both be 0. 4z equals 12, so z equals 3. So those are our 3 intercepts. And then we need to sketch. Sketching is so fun. So what we're going to do is we're going to plot these points. This is 6, 0, 0. We should label them. This will be 0, 4, 0. And this will be 0, 0, 3 right here. So if you think about it, you could take a piece of paper, that's what a plane represents, and draw it connecting all of these points, and it will go through them infinitely. We definitely have this plane that connects these points. So we have the intercepts and the sketch of the plane. This example says find the equation of the plane through points P, Q, and R. Now remember that we need a point on the plane, and we need a normal vector. So let's start with we need a normal vector. So we can do PQ and PR. So let's do PQ, vector PQ. So 3 minus 1 is 2. -1 minus 3 is -4. And 6 minus 2 is 4. And let's do PR. And 5 minus 1 is 4. 2 minus 3 is -1. 0 minus 2 is -2. Let's call this A, and let's call this B. Now remember that in order to get a normal or an orthogonal vector, what we want is we want A cross B. Yay, 12.4 coming back. So here we have IJK. Then we're going to plug in A, which is 2, -4, 4, and B, 4, -1, -2. So remember, we're looking for N. We have I times the cofactors of -4, 4, -1, -2, minus J times the cofactors of 2, 4, 4, -2, plus K times the cofactor 2, -4, 4, -1. So I have I. Remember your pluses and minuses. All right, so this gives a positive 8. This gives a -4, which is 12. So we have 12I. And then we have -4 here. And minus 16 makes -20. And there's a negative, so it makes plus 20J. And then we have -2 and minus -16. So we have plus 14K. So that means our normal vector is, let's call it 12, 20, and 14. All right, now we're supposed to find the equation of the plane. I'm going to use point P. So we're going to say the normal vector is 12. So we have 12 times x minus our p value of 1, our x sub 0, plus the second normal vector value, the second component, b, is 20. And we have y minus the y value of 3 in the point, plus 14. And we have z minus 2 equals 0. So that is our point, and they're probably going to want it in the other form. I'm sorry, this is our equation of the vector in the plane. So let's distribute. We have 12x minus 12 plus 20y minus 60 plus 14z minus 28 equals 0. So when we pull those apart, we have 12x plus 20y plus 14z minus 100 equals 0. Now you can divide that by 2. So 6x plus 10y plus 7z minus 50 equals 0. And this is our equation of our vector in a plane. And that's what we were asked to find. It just took a little bit longer because we weren't given a normal equation. We were given vectors, but we can find those. Check out this one. It says find the point at which the line with parametric equations given intersects the plane. Now all of our parametric equations, notice, are in terms of t. So if we use that to our advantage, we can find the point. So we're going to say 4 times the x value of 2 plus 3t plus 5 times the y value of -4t minus 2 times the z value of 5 plus t equals 18. This is a nice, pretty Algebra 1 problem at this point. Love it. One variable. So 8 plus 12t, hopefully I don't mess it up, minus 20t. And then we have minus 10 minus 2t equals 18. So let's collect and combine like terms. And so I have 12t minus 20t minus 2t makes -10t. And then I have 8 minus 10 makes -2. Added to the other side makes 20. So t equals -2. Now if I plug that into each of my parametric equations, then x equals 2 minus 6, which is -4, y equals -4 times -2, which is +8. And z equals 5 plus -2, which is 3. So the point is -4, 8, 3. That is the point where the parametric equations intersect the plane. Not a bad problem. It's pretty easy, pretty fun. All right, so we're going to find the angle between these two planes. And if you think about how we know angles with a cosine formula or with the sine formula. We need vectors for both. And if you paid attention and noticed, and I didn't point it out earlier, but the normal vector for this one would be the coefficients of x, y, and z. So the normal vector here is 1, 1, 1. And the normal vector here would be the coefficients as well, which is 1, -2, 3. Now, part A says find the angle between them. And I know that A dot B equals the length of A times the length of B times cosine of theta. So that means cosine of theta equals, I'm going to put this in terms of n1 dot n2 over the length of n1 times the length of n2. So I just changed my a's and b's to n's. So here I have 1 times 1 is 1, 1 times 2 is -2, and 1 times 1 is 3. And on the bottom, I have the square root of 1 plus 1 plus 1 is 3, times the square root of 1 plus 4 is 5, plus 9 is 14. So we end up with 1 minus 2 is -1 plus 3 is 2 over the square root of 42. So cosine of theta is 2 over the square root of 42. Theta equals inverse cosine of 2 over the square root of 42. And using our beautiful calculator, because I cannot do that in my head, I get 72.02 degrees. So that's an easy, finding the angle between them is not bad. It's the stuff that we learned before. And then part B, we're going to find the symmetric equations for the lines of intersection of these 2 points. Now, in order to do that, first of all, we need to find the parametric equations for the plane. So we need to start off with a normal vector. So we need a normal vector, let's call it C. So let's say vector C is normal or perpendicular to N1 and N2. Now we know that in order for that to happen, then C is equal to the cross product of N1 and N2. So here we go with our beautiful cross product again. IJK, that was a crazy looking J, but you know it should go there. And we're going to put N1 in our first spot, 1, 1, 1, and N2 in our last row, and it'll be 1, -2, 3. And then we're going to go ahead and find the cross product. So I times the cofactor 1, 1, -2, 3, plus J, and we have 1, 1, 1, 3. It's not a plus J, it's a minus J. And it's plus the vector K times 1, 1, 1, -2. I need my diagonals. I don't know if you do or not, but I need my diagonals. It's easier for me to visually see them. I know I tell you that every time, but it works. So here I have 3 and minus -2 makes plus. So we have 5i. Here we have 3 minus 1 makes a +2. So we have minus 2j because of the minus in front of the j. And we have minus 2 minus 1 makes a minus 3 times the vector of k. So that means that my normal vector is 5, -2, -3. So this vector C is perpendicular to or orthogonal to, or the normal vector to N1 cross N2. So that is what we need for our vector, but we need a point that's intersecting these planes. Let's find a point on the XY plane. So let's find our P and let's let let's find one on the XY plane. It doesn't really matter, but it's a little bit easier. So in order to do that, we're going to let z equal 0. And we're going to come back to the original equations. So let me zoom in here. So we're going to say x plus y plus 0 equals 1, and x minus 2y plus 0 equals 1. Now, I need to find a point that's on this plane. Now, we can also, at this point, let y equal 0, so it sits on the x-axis, because it doesn't really matter, it will sit on the plane. So when we do this, we get x equals 1 in both cases. So that means we have the point 1, 0, 0. So we have the normal vector up here and the point 1, 0, 0. So we can write our equation, our parametric equations. Let's go ahead and write them, and then we'll go back to the directions. So we have x equals the x sub 0, which is 1, plus 5t. And then y equals 0. We're not even going to write it, minus 2t. And z equals 0 minus 3t. Now the directions tell us to find the symmetric equations. So that means we need the three equations that are equal to each other. Let's solve this one for t, and we're going to say x minus 1 over 5. This one, t equals y over negative 2. And the last one, t equals z over negative 3. So our symmetric equation says x minus 1 over 5 equals y over negative 2 equals z over negative 3. So that's one of the symmetric equations we can find to make this equation true. Let's talk about distances. That's the next part of this lesson. So in order to find the formula from the distance from a point P1 on to the plane, we're going to let P sub 0 be any point on the plane and B be the corresponding vector. You got to look at the picture here. B be the corresponding vector from P0 to P1. Then the distance B equals x1 minus the vector x1 minus x0, y1 minus y0, z1 minus z0. And from figure 12, you can see the distance to the plane is equal to the absolute value of the scalar projection of B onto the normal vector. Now, this is not something you need to recreate again, but if you want to know where it came from, this is where it came from. So we have the component of B onto N is the distance here. So that's N dot B, the length of N dot B over the length of N. So we have N dot B, the length of N dot B to be the top here over the length of N. And when you distribute and rearrange, it becomes this. Now, if you look at the next part, it says since P sub O lies on the plane, we have this equation. So notice that this part of the equation here is equal to this part of the equation here, which is d, negative d if you take the d to the other side. So that's going to give us a really pretty definition or distance formula. So here we have the distance from the point to the plane is the following formula. D equals the length of AX1 plus BY1 plus CZ1 plus D over the length of N. Remember, this is the length of this right here on the bottom is the length of vector N. So it's not that bad of a formula to use. I showed you a little bit about where it came from, but not that big of a deal. So let's talk about how to use it. Okay, so example 8 says find the distance between these parallel planes. First, we want to look at the vectors for each of these planes. So the normal vector of this plane, let's call it n1, would be 10, 2, negative 2. And the normal vector for this plane, let's call it n2, would be 5, 1, negative 1. Notice they are parallel because the second one is half the first one, or the first one is twice the second one. So because they are multiples of one another, they are parallel. So to find the distance between them, we need to find any point on one plane and calculate its distance to the other plane. So let's pick the first plane here. Let's pick the first one over here. Let's find a point. And then we're going to use this plane here to find the distance from a point P in the plane to a given plane. All right, so when we do a point, as we did before, let's let z equal 0, and then let's go ahead and let y equal 0. And when we do, we get 10x equals 5, so x equals 1/2. So then we have the point 1/2, 0, 0. Now if we look at our distance formula, we're going to say distance equals the length of A, which is 5, times x1, which is half, plus b, that's our normal plane 1, times the distance of our y1, which is 0, plus c, which is -1, times the point, which is 0, plus d is from the normal vector, so that would be a -1, all over the length of n, which is the square root of 25 plus 1 plus 1. So if we look at the top, we're finding the length of this, and we have 5 plus 0 minus 1 is 3/2. And on the bottom, we have the square root of 27. I'm going to go ahead and call it 3 square root of 3. So we have 3 over 2 times 3 square root of 3. Let's cancel those square root of 3's. And I would like to call this 1 over 2 square root of 3. But I think WebAssign is going to have you rationalize it and call it square root of 3 over 6. So the distance between parallel planes, these two specific parallel planes, is 3 square root of 3 over 6. Check out example 9. It says in the previous example, we showed that these lines are skew, so find the distance between them. This is different than the last one because in the last two they were parallel. So we had our normal vector, but in this case we have skew lines, so we need a normal vector skew planes. So we need the normal vector between them. So let's go ahead and label n1, vector n1. Oh, can we call it vector A? Because it's not perpendicular, but it is the normal vector for the plane. So the normal vector for the plane is 1, 3, -1. Remember, it's the coefficients of t. And then here, n2, the vector perpendicular to this plane is 2, 1, 4. Now, in order to find the distance between them, we need a normal vector. We're going to call it c like we did before. And if we can find n1 cross n2, then c is perpendicular to both n1 and n2. It's perpendicular to n1, and c is perpendicular to n2. So let's find vector c, which is n1 cross n2 vectors. We're going back to our beautiful ijk, the cross product from 12.4. And here we have 1, 3, -1, and 2, 1, 4. So we have I times the cofactors of 3, -1, 1, 4, minus j times the cofactors of 1, -1, 2, 4, plus k times the cofactor, and in it we have 1, 3, 2, 1. Now let's use our matrix, and I'm going to draw my lines. And drew the -1s first. I don't know why. All right, so we have 12 minus -1 becomes +1, so we have 13i. So we have 4, positive 4, and minus a -2 makes +2. So here we have 6, so we have minus 6j. And then over here we have 1, minus 6 makes -5, so we have minus 5k. So that means our vector C is 13, -6, -5. Now we also need a point. We need a point on one of the planes. So you could let t equal 0 or anything else, or s equals 0 or anything else. So I'm going to let s equal 0 to find my point, and I'm going to be looking at the bottom here. So let's say for point P, let's let s equal 0. And when I do, x equals 0, y equals 3, and z equals -3. So then I have a point and I have a normal vector. So let's build this beautiful equation. So let's say our 13, our a parentheses x minus x sub 0 minus 6 times y minus y sub 0 plus -5, let's make it a -5, times z minus z sub 0 equals 0. So that's going to give me my beautiful equation, 13x minus 0 minus 6y plus 18 minus 5z minus 15 equals 0. So we have 13x minus 6y minus 5z plus 3 equals 0. Now remember in my distance formula, I do need that d, so I'm going to keep that value. Now we used s equals 0 to find a point, to find our equation. So what we have here is we have the equation of the plane it's got the normal vector and a point on s. So what we need now is a point on t, because when we find our distance, we need a point on one plane and the distance to the other plane. So since this is the plane that contains s, the s value for the second equation, let's let t equal 0. And then we have the point, we got to go back up. If we let t equal 0, I have 1, -2, 4. So that means we have the point 1, -2, 4. So using these two things, we can find the distance between the point on line 1 on L1 and on the first plane and the equation of the plane for the second plane. So we're going to say distance equals, I'm going to write the formula here. I have the length ax1 plus by1 plus cz1 plus d over, I'm going to call it the length of n because I like the length of n. Remember that n here equals 13, -6, -5. It's technically c. It's technically c, which is the vector that's perpendicular to both. So d equals, a is 13 times x1, which is 1, which makes 13. Do I need to write that? I guess so. Plus -6 times the y of -2 minus 5 times the z of 4 plus the d of 3 over the length of n, which is 13 squared plus 6 squared plus 5 squared. On the top, I have 13 plus 12 is 25, minus 20 is 5, plus 3 is 8. And on the bottom, I have the square root of 230. And that is our distance. Does 230 break down? 23 times 2 times 5. Nope. This is our distance between those two skew planes. And that wraps this up. If you'd like a decimal, it's 0.53. And I am pretty sure that we have done it all that you can do, all of the lessons in the exercise. Sorry for the long video, but hopefully it helps you with the lesson. Have a great day and enjoy this. I hope that you do. I like this stuff.